In the deepest reaches of space, where silence is absolute and time moves differently than it does on Earth, something beautiful is happening. It has been happening for billions of years, and it will continue long after we are gone. It is the slow, patient dance of creation itself, the transformation of clouds of cosmic dust into the worlds we see glittering in our night sky. Tonight, we are going to take a journey together. Not a hurried journey, but a slow one, moving at the unhurried pace of the universe itself. We will watch as nebulae, those vast glowing clouds of gas and dust, gradually, gently, inevitably collapse and condense. We will see stars being born in the darkness, their first light piercing through veils of cosmic fog. We will witness the formation of spinning disks around these infant suns and watch as tiny grains of dust bump and tumble and stick together, growing larger and larger over millions of years until they become the planets, moons, and asteroids that fill our solar systems. This is not a story of drama or conflict. There are no villains here, no races against time, no struggles or battles. This is simply the story of how gravity works, patiently and persistently, sculpting the universe one particle at a time. It is the story of matter finding its natural resting places, of energy flowing from hot to cold, of chaos slowly resolving into order and pattern and beauty. Picture, if you will, a cloud. Not the small, fleeting clouds that drift across Earth's blue sky on a summer afternoon, but something incomprehensibly larger. This cloud stretches across light years of space, distances so vast that light itself, traveling at 186,000 miles per second, would take years to cross from one side to the other. Within this cloud, there is hydrogen, the simplest and most abundant element in the universe. There is helium, forged in the first minutes after the Big Bang. There are heavier elements too: carbon, oxygen, iron, silicon, created in the hearts of ancient stars that lived and died before our sun was ever born. The cloud is cold, not the cold of a winter morning or even the cold of Earth's polar ice caps, but a cold that approaches absolute zero, the temperature at which atoms nearly cease their constant vibration. In some places, the temperature hovers around -440 degrees Fahrenheit, just a few degrees above the coldest temperature theoretically possible. At these frigid temperatures, atoms move slowly, lazily, conserving what little energy they have. And yet, even in this cold, there is motion. The cloud is not static. It rotates, very slowly, completing one revolution over millions of years. It expands in some places, contracts in others. Magnetic fields thread through it like invisible rivers, guiding the flow of charged particles. Radiation from distant stars pushes against it, applying gentle pressure. The gravity of nearby galaxies tugs at its edges. The cloud glows, but softly. Ultraviolet light from young, hot stars elsewhere in the galaxy strikes the hydrogen atoms, exciting their electrons, causing them to emit a gentle reddish light, the same deep crimson you might see in a sunset, but infinitely more subtle. In some regions, where oxygen is more abundant, the glow takes on a greenish or bluish tint. These colors blend and swirl together in ways that no human eye could perceive directly. creating a cosmic watercolor painting that has been developing for eons. This is a nebula. The word comes from the Latin for cloud or mist, and it is an apt description. Nebulae are among the most diffuse objects in the universe. If you could scoop up a cubic meter of material from the densest part of a typical nebula, you would find it contains fewer than 1 million atoms, far, far fewer than exist in the same volume of air you are breathing right now, which contains about 25 million trillion atoms. By Earth standards, a nebula is nearly perfect vacuum. And yet, because these clouds are so incredibly vast, their total mass can equal thousands or even millions of times the mass of our Sun. In this particular nebula, let us call it our nebula, the one we will follow on its journey, there is enough material to make not just one star, but hundreds, perhaps thousands. And around many of those stars, there will be planets. Rocky worlds and gas giants, ice moons and asteroid belts, each one a unique configuration of matter, each one following the same fundamental physical laws. But we are getting ahead of ourselves. Right now, our nebula is still a cloud, still diffuse, still mostly empty space scattered with atoms and molecules and tiny grains of dust no larger than particles of smoke. Nothing has collapsed yet. No stars have formed. There is only the cloud, glowing faintly in the darkness, rotating slowly, waiting.
Waiting for what? For the trigger, for the disturbance that will set everything in motion. In the universe, nothing lasts forever in perfect equilibrium. Everything is always changing, always responding to forces, always moving towards some new configuration. Our nebula has been drifting through space for millions of years already, part of the grand ecosystem of our galaxy. It has been shaped by supernova explosions that occurred long ago, enriched with heavy elements created in the cores of dying stars. It has been compressed and stretched by the spiral arms of the galaxy as they rotate past. It has encountered other clouds, merged with them, exchanged material. And now, something is about to happen. Somewhere nearby, perhaps a few hundred light years away, a distance that is nothing on the galactic scale, a massive star is reaching the end of its life. This star has burned through its fuel at a prodigious rate, as massive stars do. It has fused hydrogen into helium, helium into carbon and oxygen, and continued creating heavier and heavier elements in its core, building up the periodic table element by element, releasing enormous amounts of energy in the process. But there is a limit to this process. When the star's core begins to produce iron, the nuclear fusion that has supported it for millions of years can no longer continue. Iron fusion doesn't release energy, it consumes it. The core, no longer able to hold itself up against the crushing force of its own gravity, collapses in less than a second. The outer layers of the star, suddenly without support, fall inward at speeds approaching a quarter of the speed of light, then rebound in one of the most violent events in the universe, a supernova. The shock wave races outward at thousands of miles per second, carrying with it all the elements the star created during its lifetime: carbon, oxygen, neon, magnesium, silicon, iron, and dozens of others, including trace amounts of gold, platinum, and uranium, elements so heavy they can only be created in the extreme conditions of a supernova itself. And now, this shockwave is heading toward our nebula. It will take time to arrive. Even moving at thousands of miles per second, the shockwave must cross light years of space. Decades pass, perhaps centuries, but the shockwave is patient, as all cosmic processes are patient. and eventually, inevitably, it reaches the edge of our cloud. What happens next unfolds in slow motion by human standards, but rapidly by cosmic ones. The shock wave slams into the diffuse gas of the nebula, compressing it. Imagine a gentle push becoming concentrated into a smaller and smaller space. The atoms and molecules in the nebula, which had been drifting lazily with enormous distances between them, are suddenly crowded closer together. The density increases, and where there is density, there is gravity. Gravity is perhaps the most patient force in the universe. It is also the weakest of the fundamental forces, far weaker than electromagnetism, far weaker than the nuclear forces that hold atoms together. A small magnet can overcome the gravitational pull of the entire Earth when it picks up a paperclip. And yet, gravity never stops, it never fatigues, it never switches off. It works tirelessly, constantly, pulling every piece of matter toward every other piece of matter, however slightly. In the thin gas of the nebula, gravity's effects had been negligible, but now, compressed by the supernova shockwave, certain regions of the cloud have reached a critical density. In these denser pockets, gravity begins to win its slow tug-of-war against the random motions of atoms. Matter begins to pull together, ever so slightly. The denser a region becomes, the stronger its gravity, and the more material it attracts. A feedback loop has begun, a gentle, inexorable cascade toward collapse. Our journey has truly begun now. We are watching the first stirrings of star formation, the initial movements in a dance that will last millions of years and result in a newborn star surrounded by planets, warmed by its light, held in their orbits by its gravity. From nebula to planet, this is how worlds are born. Let us slow down even further. Let us watch with infinite patience as the universe does its work.
The shock wave has passed through our nebula like a stone thrown into a still pond, and the ripples are spreading. But these ripples move through space and time in ways that would seem impossibly slow to human observers. If you could watch this process unfold, speed it up millions of times, you would see waves of compression moving through the cloud, creating patterns of light and shadow, density and emptiness, as intricate as the grain in a piece of wood or the swirls in a fingerprint. In the wake of the shock wave, our nebula is no longer uniform. It has developed structure. There are regions where the gas is more compressed and regions where it remains thin. The compressed regions are where the story becomes most interesting, for these are the seeds from which stars will grow. Let us focus our attention on one such region, a pocket of gas and dust that is slightly denser than its surroundings. It is still unimaginably diffuse by Earth standards. If you could be there, you would perceive it as perfect vacuum, indistinguishable from the emptiest regions of space. But the difference in density, however slight, is enough. Gravity has noticed. Every atom in this denser region exerts a tiny gravitational pull on every other atom. Individually, these pulls are utterly negligible, far too weak to overcome the random thermal motions of the atoms themselves. But collectively, statistically, averaged over trillions upon trillions of atoms and over thousands of years, these pulls add up. The region begins to contract. The contraction is extraordinarily slow at first. Over the course of 1,000 years, the cloud might shrink by a fraction of a percent. A human observer, even if they could survive in the cold vacuum of space, would notice no change over their entire lifetime. But the universe is patient. It has all the time in the world, literally. As the cloud contracts, several things begin to happen, each following inevitably from the laws of physics, each contributing to the cascade of changes that will transform this diffuse cloud into something new. First, the rotation of the cloud becomes more noticeable. Remember that our nebula, like most structures in space, was already rotating slowly, a legacy of the turbulent motions and gravitational interactions that shaped it. As the cloud contracts, conservation of angular momentum, the same principle that causes an ice skater to spin faster when they pull their arms inward, causes the rotation to speed up. Over millions of years, what was once an imperceptibly slow rotation becomes more and more rapid. The rotation affects the shape of the cloud. Centrifugal force, the apparent outward force experienced by objects in rotating systems, begins to have an effect. This force is weakest at the poles of rotation and strongest at the equator. As a result, the cloud begins to flatten. What started as a roughly spherical blob of gas slowly becomes more disc-like, bulging at the middle, flattened at the top and bottom. This is the same shape taken by galaxies, by planetary rings, by the disk of our own solar system. It is a universal consequence of rotation and gravity working together. Second, as the cloud contracts, it becomes warmer. This might seem counterintuitive. After all, we typically think of compression as something that happens in engines and pumps, not in the cold vacuum of space. But the principle is the same. When gas is compressed, the atoms move faster, and faster-moving atoms mean higher temperature. This is not yet enough to create noticeable heat. The cloud is still extraordinarily cold by everyday standards, but the temperature is rising, degree by degree, from negative 440 degrees Fahrenheit toward warmer, though still frigid, values. Third, the increasing density allows new chemical processes to occur. In the thinnest parts of the original nebula, atoms rarely encountered each other, but in these denser regions, collisions become more frequent. Hydrogen atoms, the most abundant element, can collide and stick together to form molecular hydrogen, H2, two hydrogen atoms bonded together. This is a significant development because molecular hydrogen can absorb and emit radiation in ways that single atoms cannot, allowing the cloud to cool more efficiently in some regions while trapping heat in others. More complex molecules begin to form as well. Carbon atoms combine with oxygen to form carbon monoxide, one of the most common molecules in space. Oxygen combines with hydrogen to form water, though not the liquid water we are familiar with. At these temperatures, water exists only as ice, coating the tiny dust grains that drift through the cloud. Nitrogen combines with hydrogen to form ammonia, methane forms, and formaldehyde, and dozens of other simple organic molecules.
These molecules are not alive, not even close, but they are the chemical building blocks from which billions of years later, after many more transformations and concentrations, life might eventually emerge. Every molecule of water in your body, every carbon atom in your cells was once drifting in a cloud like this, in the cold darkness between the stars. The dust grains themselves play a crucial role in this process. These tiny grains, most are smaller than the wavelength of visible light, which is why they scatter light and create the colorful glows we see in images of nebulae. They are made of various materials. Some are carbon-based, similar to soot. Others are silicates, like microscopic grains of sand. Still others are made of iron or other metals. In the cold environment of the nebula, these grains serve as surfaces on which atoms can meet and bond. A hydrogen atom drifting through space might collide with a dust grain and stick to it, held in place by weak electrical forces. Another hydrogen atom might collide with the same grain, and in the slow cosmic dance of probability, happen to land next to the first. On the surface of the grain, facilitated by its presence, the two atoms can combine to form molecular hydrogen. The newly formed molecule then drifts away, and the grain continues its journey, ready to facilitate the formation of more molecules. This process is happening everywhere in the contracting cloud, on countless trillions of dust grains, creating molecules at a rate that would be dizzying if we could perceive it happening. But from our human perspective, watching this section of the nebula,
everything still seems almost motionless, almost unchanging. The cloud glows its faint colors, reds and blues and greens, shifting slowly as different elements are excited by radiation from distant stars. The dust creates dark lanes and patches where it is thick enough to block the light from behind. The whole structure rotates, slowly flattening into a disk. Tens of thousands of years pass. The cloud continues to contract. It is now perhaps a tenth the size it was when the supernova shockwave first compressed it, but it is still vast beyond human comprehension, several light years across, large enough to contain our entire solar system hundreds times over. Within this larger cloud, smaller structures are forming. Just as the supernova shockwave created density variations in the original nebula, the turbulent, chaotic motion of gas within the contracting cloud creates new variations. Eddies and streams of gas flow in complex patterns. Some regions become denser than others purely by chance, and these denser regions begin their own gravitational collapse, creating smaller clouds within the larger cloud. This is how nebulae often give birth to multiple stars rather than just one. The original cloud fragments into dozens or hundreds of smaller clumps, each one collapsing under its own gravity, each one potentially destined to become a star. Some of these clumps will be massive, containing enough material to create bright, hot blue stars that burn fiercely but briefly. Others will be smaller, creating dimmer, cooler red stars that will burn steadily for trillions of years. Still others will be too small to create stars at all, collapsing into objects known as brown dwarfs, failed stars that never quite achieved the temperatures necessary to ignite nuclear fusion in their cores. Let us follow one particular clump, one particular collapsing region within our nebula. This clump contains roughly the mass of our Sun, about 333,000 times the mass of Earth, or approximately 2 trillion kilograms, if such numbers have any meaning at this scale. This is the clump that will become our star, and eventually the planets that orbit it. The clump is several light months across at this point, far enough that light would take months to travel from one side to the other. It is still very cold, still very diffuse, but it is growing denser and warmer as it contracts. The center of the clump, where the gravity is strongest and the compression is greatest, is becoming noticeably warmer and denser than the outer regions. The collapse is accelerating now. Remember that the denser a region becomes, the stronger its gravity, and the faster it pulls in more material. What took tens of thousands of years at the beginning now happens in thousands of years, and the pace continues to quicken. As the clump contracts and rotates faster, it flattens even more dramatically than the larger cloud did. The poles of rotation, where there is little centrifugal force to oppose gravity, collapse rapidly inward, but at the equator, the rotation creates an outward force that partially counteracts gravity. Material falling inward from above and below the rotation axis cannot easily cross the equatorial plane, so it settles into a rotating disk around the central condensation. This disk is crucial. This is where the planets will form, but that is still far in the future. For now, the disk is just a flattened concentration of gas and dust rotating around a central point that is growing denser and hotter with each passing millennium. At the very center of the collapsing clump, conditions are becoming extreme by nebula standards, though still mild by stellar standards. The density has increased to the point where atoms are no longer separated by vast gulfs of empty space. They are crowded close together, colliding frequently, exerting pressure on one another. The temperature has risen from the negative hundreds of degrees Fahrenheit to merely very cold, then to merely cold, then to temperatures approaching the freezing point of water. This central region, destined to become the core of a new star, is now opaque. Countless dust grains floating in the dense gas absorb any light trying to pass through, creating a dark, hidden place where the final stages of stellar birth will occur out of sight.
Around this opaque core, the rotating disk of gas and dust extends outward for distances that will eventually become the size of planetary orbits. The disk is thicker near the center and thinner at the edges, with material constantly spiraling inward, drawn by the gravity of the growing core. Friction between different parts of the disk causes it to heat up slightly, and this heat is radiated away into space as infrared light, invisible to human eyes but detectable by specialized instruments. If we could see this system now, at this intermediate stage of formation, we would see something remarkable: a dark, dusty disk glowing faintly in infrared light with a dense, hot core at its center. This is what astronomers call a protostar, not yet a star, but well on its way to becoming one. It is still gathering mass from its surroundings, still contracting, still heating up, but the basic structure is in place. The nebula phase of our story is coming to an end. What began as a vast, diffuse cloud of gas and dust, disturbed by a supernova shockwave, has fragmented and collapsed. Multiple clumps throughout the nebula are following similar paths, each one creating its own protostar, its own disk. Some of these will be near neighbors, close enough to influence each other gravitationally or even to share material. Others will be more isolated, evolving independently. But everywhere in this stellar nursery, the same processes are at work. Gravity pulls matter together. Rotation flattens it into disks. Compression heats the central cores. The universe, following the mathematical precision of physical law, is sculpting stars and the beginnings of planetary systems from formless clouds. Hundreds of thousands of years have passed since the supernova shockwave first disturbed our nebula. The initial cloud is no longer recognizable. In its place is a cluster of young stellar objects, each one surrounded by its own rotating disk of material. Some are more massive, some less. Some are contracting rapidly, others more slowly, but all are following the same fundamental path, the same recipe for star formation that has been repeated countless times throughout the universe's history. Our particular protostar, the one we have chosen to follow, is approaching a critical threshold. Its core is now so dense and so hot that new physics is beginning to take over. The gentle processes of molecular formation and dust grain chemistry are being replaced by something far more energetic. The protostar is about to wake up, to announce its presence to the cosmos, to begin the next phase of its evolution. But we are not quite there yet. For now, the protostar remains dark and hidden, wrapped in its cocoon of dust, accumulating mass, growing denser and hotter. The disk around it rotates steadily, a flat carousel of gas and dust orbiting in the darkness, waiting. The nebula has done its work. It has concentrated matter, created the conditions for stars to form, and set the stage for everything that follows. From here, the story becomes more focused, more concentrated, as we zoom in on our particular protostar and watch as it takes its first faltering steps toward becoming a true star. The protostar sits at the center of its disk, hidden from view, wrapped in layers of dust and gas. But inside this dark cocoon, something extraordinary is happening. The temperature is rising. For hundreds of thousands of years, the core of the protostar has been growing hotter as it contracts. This is not heat from any chemical reaction or combustion. There is no fire here, no burning in the conventional sense. This is heat from gravitational compression, from the simple fact that when gas is squeezed into a smaller space, its atoms move faster, and faster moving atoms mean higher temperature. The temperature at the core has now reached thousands of degrees. The material here is no longer a gas in the ordinary sense. It has become a plasma, a state of matter where electrons are stripped from their atoms, creating a mixture of positively charged nuclei and negatively charged free electrons, all moving at tremendous speeds, colliding constantly. At these temperatures and pressures, the chemical bonds that held molecules together have long since broken apart. There is no molecular hydrogen here anymore, no water ice, no carbon monoxide. There are only bare atomic nuclei, mostly hydrogen, the simplest nucleus, consisting of a single proton, but also some helium nuclei, consisting of 2 protons and 2 neutrons bound together. The pressure at the core is immense. The weight of all the material above presses down with crushing force. Imagine standing at the bottom of an ocean that is not a few miles deep, but thousands of miles deep, with layer upon layer of material pressing down from above. That is the environment in the protostar's core. Under these extreme conditions, temperatures reaching millions of degrees, pressures millions times greater than Earth's atmosphere, something remarkable becomes possible. The hydrogen nuclei, despite being positively charged and therefore repelling each other electrically, can be forced close enough together that the strong nuclear force, which operates only at extremely short distances, can take over and bind them together. This is nuclear fusion, the process that powers stars, the same process that occurs in hydrogen bombs, but controlled and sustained over millions or billions of years. When 2 hydrogen nuclei fuse together, they create a helium nucleus, and in the process, a tiny amount of mass is converted into energy, according to Einstein's famous equation, E equals mc squared. That tiny amount of mass, multiplied by the speed of light squared, an enormous number, yields a tremendous amount of energy. In the core of our protostar, fusion is beginning. At first, only a few fusion reactions occur per second, scattered randomly through the core, as particularly energetic hydrogen nuclei happen to collide with enough force to overcome their electrical repulsion. But as the core continues to contract and heat up, the fusion rate increases. More and more hydrogen nuclei are reaching the speeds necessary for fusion. The energy released by these reactions heats the core further, which increases the fusion rate, which releases more energy, a feedback loop. But unlike the runaway collapse driven by gravity, this is a stabilizing feedback loop. The energy released by fusion creates an outward pressure that begins to counteract the inward pull of gravity. For hundreds of thousands of years, gravity has been winning the battle, pulling the protostar ever smaller and denser. But now, fusion has entered the fight. The protostar's contraction slows, then stops. An equilibrium is reached. Gravity pulling inward, fusion pressing outward, the 2 forces perfectly balanced. This is the moment of birth. This is when a protostar becomes a true star. The process has taken perhaps 1,000,000 years from the initial collapse of the cloud to this moment, a blink of an eye in cosmic terms, but an eternity by human standards. Our star has turned on. Deep in its core, hidden from view by layers of plasma and dust, hydrogen is fusing into helium at a rate of hundreds of millions of tons of matter into pure energy every single second. This energy radiates outward from the core in the form of high-energy photons, gamma rays, the most energetic form of light. But these gamma rays do not travel directly from the core to the surface and then out into space. The interior of the star is far too dense for that.
Instead, each photon travels only a short distance before it collides with an electron or a nucleus, is absorbed, and then re-emitted in a random direction. The photon scatters and bounces like a pinball, taking a chaotic, wandering path outward. This journey from the core to the surface is extraordinarily long, not in distance but in time. Although the star's radius is only about 1,000,000 kilometers, a distance that light could cross in a few seconds if traveling in a straight line, the countless absorptions and re-emissions mean that it takes hundreds of thousands of years for energy generated in the core to work its way to the surface. The light we see from our sun today was created in nuclear fusion reactions that occurred during the Stone Age of human civilization. As the energy works its way outward, it changes form. The high-energy gamma rays from the core are absorbed and re-emitted so many times, each time giving up a bit of energy to the material around them, that by the time they reach the surface, they have been degraded into lower-energy photons, ultraviolet light, visible light, and infrared radiation. This is the light that will eventually illuminate planets, warm their surfaces, drive their weather, and potentially make life possible. But we are getting ahead of ourselves. Our star is newborn, still surrounded by the disk of material from which it formed. This disk is still feeding the star, still adding to its mass. Material from the disk spirals inward, falling onto the star's surface, releasing even more energy as it impacts and merges with the stellar material. The star is not yet stable, not yet settled into the calm, steady existence it will maintain for billions of years. Young stars are turbulent, violent places. Powerful magnetic fields, generated by the motion of charged plasma in the star's interior, thread through the stellar surface and out into the surrounding space. These magnetic fields can become twisted and tangled, and when they snap and reconnect, they release enormous amounts of energy in stellar flares, bursts of light and streams of charged particles far more powerful than anything the mature star will produce. The newborn star also generates strong stellar winds, streams of charged particles flowing outward from its surface at speeds of hundreds of kilometers per second. These winds are much more powerful than the solar wind produced by the mature sun, and they play a crucial role in the evolution of the surrounding disk. The wind and the radiation from the star begin to push against the inner regions of the disk, heating the gas and dust, driving it outward, or causing it to evaporate entirely. The disk, which had been feeding the star, is now being pushed back, being eroded by the very star it created. This is the beginning of the end for the disk, but its work is not yet done. The disk still contains far more mass than will end up in planets. Most of it will eventually be blown away into space, but the small fraction that remains will be enough. Let us take a moment to appreciate what has occurred. From a cold, diffuse cloud of gas and dust, gravity and physics have created a ball of plasma hot enough to sustain nuclear fusion. This ball of incandescent gas, roughly 1,000,000 kilometers in diameter, will shine steadily for billions of years, fed by the vast reserves of hydrogen fuel in its core. It has joined the community of stars, adding its light to the countless others scattered through the galaxy. Our star is still young, still settling into its final mass and luminosity. Over the next few tens of millions of years, it will continue to accrete material from its disk, growing slightly larger and more luminous. It will also continue to lose mass through its powerful stellar wind, which carries away material from its outer layers. These competing processes, accretion and mass loss, will eventually balance out, and the star will reach its final stable configuration. The star's final mass will determine its fate. If it is very massive, containing 10 or 20 or even 100 times as much material as our Sun, it will burn bright and hot and blue, fusing hydrogen at a prodigious rate, exhausting its fuel in just a few million years before exploding as a supernova, contributing its elements back to the interstellar medium to be incorporated into future generations of stars. If it is less massive, like our Sun, it will burn more slowly and steadily, remaining on what astronomers call the main sequence for 10 billion years or more, before eventually swelling into a red giant and then gently shedding its outer layers to become a white dwarf. Our particular star, the one we are following, will be similar to our Sun, neither the most massive nor the least, but somewhere in the comfortable middle, destined for a long and stable existence. This is fortunate because such stability is necessary for what comes next. Planets can form around stars of any mass, but the calmer environment around a Sun-like star provides better conditions for the complex processes of planet formation.
The newborn star illuminates its surroundings now. The thick cocoon of dust that hid the protostar is being blown away by the stellar wind and evaporated by the star's radiation. For the first time, visible light from the star's surface can escape into space. If there were observers elsewhere in the galaxy with telescopes powerful enough to see this stellar nursery, they would notice a new point of light, a new star joining the cosmic community. Around the star, the disk persists, but it is changing. The inner regions, closest to the star, have been largely cleared of gas. The intense radiation and stellar wind have either driven the gas outward or caused it to fall onto the star. What remains in the inner disk is mostly dust, solid particles of rock and metal that are less affected by radiation pressure and more resistant to evaporation. Farther out from the star, beyond a distance astronomers call the frost line, conditions are different. Here, the star's heat is less intense, and temperatures are low enough that water can exist as ice rather than vapor. This frost line, roughly where the asteroid belt would be in our solar system, marks an important boundary. Inside it, planets will be rocky and metal-rich. Outside it, planets can incorporate vast amounts of ice and, given enough time, can accumulate huge atmospheres of hydrogen and helium, becoming gas giants. The disk is still massive, still containing perhaps 100 times the mass of Earth, scattered through a region billions of kilometers across. It rotates around the star in orderly fashion, following Kepler's laws. Material closer to the star orbits faster, material farther out orbits more slowly. The disk is thin, only a few million kilometers from top to bottom, but it extends outward for billions of kilometers in the plane of rotation. Within this disk, the material is not uniformly distributed. There are variations in density, regions where dust and gas are slightly more concentrated, others where they are more sparse. These variations arise from turbulence in the disk, from the gravitational influence of other nearby protostars, from instabilities in the rotating structure itself. The dust particles in the disk are in constant motion, orbiting the star, colliding with each other, occasionally sticking together in gentle, slow-motion collisions. The star continues to shine, its fusion reactions proceeding steadily, converting hydrogen to helium in its core, releasing energy that flows outward and escapes into space. The star has found its equilibrium, has settled into a stable configuration that it will maintain with only minor variations for billions of years to come. Around it, the disk waits. The stage is set for the next act of creation. The star has been born, has turned on its fusion furnace, and has cleared a space for itself in the material from which it formed. Now, the disk, that flat, rotating carousel of dust and gas, will become the birthplace of worlds. The stellar birth is complete.
From nebula to protostar to star, the transformation has taken roughly 1,000,000 years, a cosmic instant. But the creation of planets will take longer, will require patience even by cosmic standards, will demand that tiny dust grains somehow grow, collision by collision, into objects as massive as Earth or Jupiter. That is where our story turns next. The star is born and shining. Now it is time for the disk to work its slow magic, for the dance of dust and ice to begin, for gravity to operate on a smaller scale, building worlds grain by grain, collision by collision, orbit by orbit. The disk around our newborn star stretches across billions of kilometers of space, a vast, flat expanse of dust and gas, rotating in orderly fashion around the central light. From a distance, if you could see it edge on, it would appear as a dark band bisecting the bright point of the star, its thinness making it seem almost like a line drawn across space. From above or below, it would resemble a spiral galaxy in miniature, though without the elegant spiral arms, just a gradually dimming glow extending outward from the central brightness. This is what astronomers call a protoplanetary disk, and it is the birthplace of planets. Every planet in our solar system, every moon, every asteroid and comet formed in a disk like this one orbiting our young sun 4.5 billion years ago. And around countless other stars throughout the galaxy and the universe, similar disks are or have been doing the same work, creating the diversity of planetary systems we are only now beginning to discover. The disk is not a static structure. Everything in it is moving, rotating around the star, but not everything rotates at the same speed. Material close to the star completes an orbit in a matter of weeks or months, while material farther out takes years or even centuries to complete one circuit. This differential rotation creates friction between adjacent regions of the disk, and this friction has important consequences. As gas and dust at different orbital distances slide past each other, friction between them converts some of their orbital energy into heat. This heat is radiated away into space as infrared light, causing the material to gradually lose energy and spiral inward toward the star. Over millions of years, this process causes much of the disk's material to either fall onto the star or be pushed outward by the star's radiation and wind, gradually depleting the disk. But before the disk dissipates entirely, a process that takes several million years, it has time to build planets. And that process begins with the smallest of scales, with individual dust grains floating in the void. These grains are in constant motion, each one following its own orbit around the star, but because they are so small and so close together in the disk, they frequently encounter each other. When two grains collide, several things can happen. If they are moving too fast relative to each other, they might simply bounce apart unchanged. If they collide at very high speed, they might shatter, breaking into smaller pieces. But if they collide gently enough at just the right relative speed, something wonderful can happen. They can stick together. The sticking is not dramatic. There are no chemical bonds forming, no welding or melting. Instead, the grains stick together through van der Waals forces, weak electrical attractions between molecules that become significant only when surfaces are very close together. These are the same forces that allow a gecko to walk up a wall or that make dust cling to a window. On the scale of micrometers, these forces are enough to make colliding grains adhere to each other. Once two grains have stuck together, they become a slightly larger object with slightly more mass and slightly more gravity. When this larger object collides with other grains, it can capture them as well, growing larger still. This is the first stage of planet formation, the growth of dust grains into larger and larger aggregates through gentle collisions and sticking. This process is happening everywhere in the disk simultaneously on countless trillions of grains. In the denser parts of the disk, where collisions are more frequent, process proceeds faster. In the sparser regions, it proceeds more slowly. But everywhere, grain by grain, collision by collision, larger objects are forming. Over thousands of years, the aggregates grow from microscopic specks to the size of pebbles, then to the size of rocks, then to the size of boulders. They are loose, fluffy structures, more like dust bunnies than solid rocks, with lots of empty space between the original grains. But they continue to grow, sweeping up smaller particles as they move through the disk, gradually becoming denser as the weight of accumulated material compresses the interior. This is a gentle process, slow and patient. There is no violence here, no dramatic events, just the steady accumulation of material following the laws of physics. The objects are still tiny by planetary standards. Even after thousands of years of growth, the largest are only meters across, perhaps the size of a house, but they are growing, and their growth is accelerating. As the objects become larger, their gravity becomes more significant. An object a few meters across has negligible gravity, not enough to pull in nearby particles, but an object a kilometer across has enough gravity to noticeably affect the trajectories of nearby particles, drawing them in, increasing the effective cross-section for collisions. This is another feedback loop. The larger an object becomes, the more effectively it can grow, and the faster it becomes larger. Objects in the disk are not all the same size. Some, by chance, have grown larger than their neighbors. These larger objects have an advantage. They can attract more material, they can survive collisions that would shatter smaller objects, and they can stir up the surrounding dust, creating turbulence that brings even more material within their reach. Over time, these larger objects grow faster than the smaller ones, and the size distribution of objects in the disk begins to spread out. There are still countless small pebbles and rocks, but there are also increasingly large boulders and small mountains of accumulated material. We need to pause here and appreciate the timescales involved. We are no longer talking about thousands of years, but hundreds of thousands, even millions of years. The process of building planets from dust is slow beyond human comprehension. If you could watch this process unfold at human speeds, you would see essentially nothing happening, just a disk of dust and gas rotating endlessly with no apparent change from day to day or year to year. Only when time lapsed over millennia would you begin to see the dust clumping, the formation of larger objects, the gradual clearing of the disk. The disk is also evolving in other ways. The gas, which makes up most of the disk's mass, is gradually being lost. Some of it falls onto the star, some is blown away by the stellar wind, and some is stripped away by the ultraviolet radiation from the star and from nearby hot stars in the stellar nursery. The gas disk has a limited lifetime, perhaps 3 to 10 million years, before it is completely dispersed. This creates a time constraint for planet formation. Gas giant planets like Jupiter and Saturn require vast amounts of hydrogen and helium, which they can only acquire while the gas disk still exists. If a planet is to become a gas giant, it must grow large enough to capture gas from the disk before the gas is gone. This means it must first build a solid core massive enough to gravitationally hold on to a thick atmosphere, a core at least 10 times the mass of Earth. Building such a core takes time, and the clock is ticking. In the inner part of the disk, near our star, the conditions are too hot for gas giant formation. The star's heat and radiation pressure keep the light elements, hydrogen and helium, in constant motion, making it difficult for them to be captured by forming planets. Here, planets will be rocky and relatively small, built from the materials that can withstand the heat, silicates, metals, and small amounts of more volatile compounds. Farther out, beyond the frost line, conditions are different. Here, temperatures are low enough that water ice is stable and water is relatively abundant in the universe. The presence of ice dramatically increases the amount of solid material available for planet building. Inside the frost line, there might be enough material to build a few Earth-sized rocky planets. Outside it, there is enough material to build cores massive enough to capture gas and become giants. Let us watch as the objects in the disk continue to grow. Millions of years have passed since the star was born. The disk has thinned considerably, much of its gas has been lost, and much of its dust has either fallen onto the star or been incorporated into growing objects. But there is still plenty of material remaining, and the largest objects in the disk have now reached impressive sizes. In the inner disk, the largest objects are perhaps the size of our moon, a few thousand kilometers across. They are made of rock and metal, dense and solid, products of countless collisions that have compressed and heated the material, driving off any volatile compounds and leaving only the most refractory substances. These are the beginnings of terrestrial planets, worlds like Mercury, Venus, Earth, and Mars. In the outer disk, beyond the frost line, the largest objects are even more impressive. Here, cores as large as 10 Earth masses have formed, built from a mixture of rock, metal, and ice. These massive cores have enough gravity to begin capturing gas from the surrounding disk. Hydrogen and helium, still abundant in this region, begin to fall onto these cores, forming thick atmospheres that grow larger and larger as more gas is captured. This is the formation of gas giants, and it is a runaway process. The more gas a core captures, the more massive it becomes, and the stronger its gravity, which allows it to capture even more gas. Within a few 100,000 years, a core that started with 10 Earth masses can grow to hundreds of Earth masses, with the vast majority of that mass being hydrogen and helium gas surrounding a relatively small solid core. Not all cores become gas giants. Some form too late, after most of the gas has been dispersed. Others form in regions where the gas density is too low, or where gravitational disturbances from nearby objects disrupt the accretion process. These cores remain as ice giants, smaller than Jupiter or Saturn, but still massive compared to rocky planets, made primarily of water, methane, and ammonia ices with thick atmospheres of hydrogen and helium. The disk is becoming crowded now with these growing objects, and their gravitational interactions are becoming more important. Objects whose orbits bring them near each other can perturb each other's paths, causing their orbits to change slightly. Over time, these perturbations can cause orbits to become more eccentric rather than circular, or to become tilted relative to the plane of the disk. Sometimes gravitational interactions are strong enough to cause objects to be ejected from the system entirely, flung outward at high speed by a close encounter with a more massive body. Other times, objects are scattered inward toward the star, where they might collide with the star itself or with other objects in the inner disk. Collisions between large objects are now possible, and when they occur, they are spectacular. Two moon-sized bodies, each traveling at several kilometers per second, colliding and merging in a burst of heat and violence. These collisions can shatter both objects, creating clouds of debris that will later reaccumulate, or they can result in a merger, creating an even larger object from the combined mass of both. The disk is also developing gaps and rings. Regions where large objects have formed are cleared of smaller debris. The large object's gravity has swept up everything nearby. Other regions where gravitational resonances with large planets create instabilities are also cleared, with material either scattered away or accumulated into the resonant regions. The once smooth and continuous disk is becoming structured, divided into distinct zones separated by gaps. 5 to 10 million years have passed since the star was born. The gas disk is nearly gone now, with only thin wisps remaining in the outermost regions. The disk of solid material, dust, pebbles, boulders, and larger objects, persists longer, but it too is thinning. Much of the material has been incorporated into the growing planets, and much has been lost, either falling onto the star or being ejected from the system entirely. The protoplanetary disk has done its work. It has served as the medium through which planets formed, the reservoir of material from which they drew, the environment that shaped their composition and orbits. But the disk's time is ending. The star has matured, the planets are growing, and the remaining debris is being cleared away through collisions, accretion, and ejection. What remains is no longer a smooth disk, but a planetary system in its infancy, a collection of growing planets, each in its own orbit, along with vast numbers of smaller objects, asteroids, comets, and debris that will continue to collide and evolve for millions of years to come. The disk phase is over. The planet formation phase is fully underway. And our story now shifts focus from the disk itself to the individual worlds that are emerging from it, each one following its own path, shaped by its location, its composition, and the chaotic gravitational dance of the forming solar system. The objects we have been watching grow, patiently and slowly, can now be called planets, though they are not yet finished. They have reached sizes comparable to the planets we know, some Earth-sized, some much larger, some smaller, and they have cleared their orbital zones of most of the smaller debris. But they are still young, still evolving, still experiencing the violent collisions and dramatic transformations that will determine their final characteristics. Let us begin in the inner part of the planetary system, close to the star, where rocky planets are forming. Here, several large objects orbit in relatively close proximity to each other, each one a few thousand kilometers in diameter, each one made primarily of rock and metal. These are planetary embryos, and they are on a collision course. The orbits of these embryos are not perfectly stable. Small gravitational perturbations caused by interactions with each other and with the remaining debris in the system cause the orbits to slowly change over time. Some orbits become more elliptical, others become more tilted. Eventually, inevitably, orbits cross, and when they do, collisions become possible. A collision between two planetary embryos is one of the most energetic events that can occur during planet formation. These are not gentle encounters like the collision of dust grains. These are massive objects, each containing trillions of tons of rock and metal, traveling at speeds of several kilometers per second, speeds at which kinetic energy is enormous. When two embryos collide, the impact releases as much energy as billions of nuclear weapons detonating simultaneously. The entire surface of both objects instantly vaporizes. Rock is heated to thousands of degrees and turns to plasma. Shock waves propagate through the interiors, shattering solid rock, melting vast regions. If the collision is head-on, both objects may be completely destroyed, reduced to clouds of molten and vaporized debris that will later recondense into new objects. But most collisions are not head-on. More commonly, they are glancing blows, where one object sideswiped another. In such collisions, part of each object may be destroyed or ejected into space, while the main masses merge together, forming a larger, irregularly shaped body that will gradually relax into a spherical shape under its own gravity. These giant impacts are how the terrestrial planets grew to their final sizes. The Earth, for example, is thought to have formed through a series of collisions with dozens of smaller embryos over a period of tens of millions of years. The final major collision, occurring perhaps 50 million years after the Sun formed, involved an object about the size of Mars striking the proto-Earth. This impact was so violent that it ejected a huge amount of material into orbit around Earth, material that later coalesced to form the Moon. After each giant impact, the resulting planet is a hellish place. The surface is an ocean of molten rock, a magma ocean kilometers deep, glowing red-hot, with a temperature of thousands of degrees. The atmosphere, if any survived the impact, is a thick steam of vaporized rock and metal. The heat from the impact, combined with the heat from the decay of radioactive elements in the planet's interior, keeps the magma ocean molten for millions of years. Slowly, very slowly, the planet cools. Heat radiates away into space, and the surface begins to solidify, forming a thin crust that floats on the underlying magma. But the interior remains molten for much longer, and convection currents in the liquid rock carry heat from the interior to the surface, where it can be radiated away. During this cooling phase, the planet undergoes differentiation. The denser materials, primarily iron and nickel, sink toward the center, forming a metallic core. The lighter materials, silicates, oxides, rise toward the surface, forming the mantle and crust. This separation is driven by gravity and facilitated by the liquid state of the rock. Over millions of years, the planet reorganizes itself into layers: a dense iron core at the center, a thick rocky mantle surrounding it, and a thin, rigid crust at the surface. This is the structure we see in Earth and the other terrestrial planets today, but it took a long time to achieve. The process of differentiation, of giant impacts and cooling and reorganization, took perhaps 100 million years, a significant fraction of the total time the solar system has existed. While the inner planets are being assembled through violent collisions, the outer planets, the gas giants, are undergoing their own transformations. These planets formed earlier and faster, taking advantage of the abundant material beyond the frost line and the presence of the gas disk. By the time the terrestrial planets are still embryos, the gas giants have already reached close to their final masses. But they are not yet in their final orbits. The early solar system was more crowded than it is today, with planets and debris scattered throughout. Gravitational interactions between planets and the remaining disk material cause the planet's orbits to change over time, a process called planetary migration. A planet orbiting through a disk of gas and dust experiences gravitational forces from that material. Material interior to the planet's orbit pulls it inward, while material exterior to the orbit pulls it outward. Depending on the distribution of material, the net effect can cause the planet to spiral inward toward the star or to move outward away from it. Jupiter, the most massive planet, likely migrated inward during its formation, moving from perhaps 3.5 astronomical units, 3.5 times Earth's distance from the Sun, to its current position at about 5 astronomical units. This inward migration had profound effects on the inner solar system, stirring up the orbits of smaller bodies, scattering asteroids and planetary embryos, and potentially preventing a planet from forming in what is now the asteroid belt. Later, interactions between Jupiter and Saturn may have caused both planets to reverse their migration and move outward. This event, sometimes called the Grand Tack, would have further scrambled the orbits of objects in the solar system, sending some toward the Sun, others toward the outer reaches of the system. The ice giants, Uranus and Neptune, also migrated, likely moving outward from their formation locations to their current distant orbits. This outward migration was dramatic, carrying these planets through regions filled with icy debris, scattering that debris both inward and outward. Some of this debris was sent into the inner solar system, where it bombarded the newly formed terrestrial planets in what is known as the late heavy bombardment. Other debris was sent outward, forming the Kuiper Belt and the Oort cloud, vast reservoirs of icy bodies in the distant reaches of the solar system. All of this migration and scattering and bombardment took place over tens to hundreds of millions of years. The early solar system was a chaotic, dynamic place, with planets moving, debris flying everywhere, and frequent collisions occurring. It was nothing like the stable, orderly system we see today. But gradually, over time, the chaos subsided. The gas disk was completely gone, dispersed into interstellar space. Most of the solid debris was either incorporated into planets, ejected from the system, or sequestered in stable reservoirs like the asteroid belt and Kuiper belt. The planet's orbits stabilized, settling into configurations that have remained largely unchanged for billions of years. Let us take stock of what has formed. In the inner system, there are several rocky planets, perhaps 4 or 5, depending on how many embryos manage to avoid being scattered away or colliding with the sun. These planets are dense, made of rock and metal, with thin atmospheres, if any. Their surfaces are scarred by impact craters, evidence of the final stages of accretion when remaining debris rained down on them. In the middle region, there may be a belt of asteroids, leftovers from planet formation that never accumulated into a larger body, perhaps prevented from doing so by Jupiter's gravitational influence. Farther out, there are the gas giants, massive planets with thick atmospheres of hydrogen and helium surrounding relatively small rocky cores. These planets dominate the outer system, containing most of the mass of all the planets combined. Their gravity shapes the orbits of everything around them. Beyond the gas giants, there may be ice giants, smaller but still substantial, made primarily of ices and rocks with thinner atmospheres. And beyond them, in the cold, distant reaches, there are countless small icy bodies, leftovers from planet formation, waiting in frozen orbits that will remain essentially unchanged for the entire lifetime of the star. The planets are not alone. Many have captured moons during their formation, either through collisions that ejected material into orbit, like Earth's moon, or by gravitationally capturing passing objects, like many of Jupiter's outer moons. These moons are worlds in their own right, some of them large enough to have undergone differentiation and geological activity. The planetary system is not static even after the main phase of formation is complete. Collisions still occur, though they are much rarer now. Asteroids and comets occasionally strike planets, delivering water and organic compounds, perhaps even contributing to the origin of life on favorable worlds. Gravitational interactions continue to slowly modify orbits, though on timescales of millions or billions of years. The planets themselves continue to evolve. Their interiors cool gradually, at rates dependent on their size and composition. Smaller planets cool faster and may become geologically dead, with solid interiors and no tectonic activity. Larger planets cool more slowly and may remain geologically active for billions of years, with molten cores generating magnetic fields and convecting mantles driving plate tectonics and volcanic activity. Atmospheres evolve as well. Some planets may lose their atmospheres entirely, stripped away by the stellar wind or by the planet's low gravity. Others may develop thick atmospheres through volcanic outgassing, as gases dissolved in the planet's interior are released through volcanic eruptions. Still others may have their atmospheres transformed by life, if life arises, with biological processes removing or adding various gases over time. 100 million years have passed since the star was born. The planetary system has reached a recognizable form. The planets are in stable orbits, the debris has been largely cleared away, and the system has settled into a configuration that will persist, with only minor modifications, for billions of years to come. Planet formation is essentially complete. What began as tiny grains of dust in a protoplanetary disk has become a diverse collection of worlds, each one unique, each one shaped by its particular history of accretion, collision, differentiation, and migration. Some are rocky and barren, others are shrouded in thick atmospheres, still others are giant balls of gas with perhaps hidden cores of rock and ice at their centers. The universe has worked its slow magic once again, following the mathematical precision of physical law, transforming simple ingredients, gas and dust, into complex structures, planets and moons and solar systems. And our star now has a family, a collection of worlds orbiting around it, bound together by gravity, illuminated by its light. The planetary system is young but formed. The major bodies have achieved their final masses and settled into orbits that, while not yet perfectly stable, are close to their final configurations. But the system is not yet mature. It is still a dynamic, evolving place, and it will undergo significant changes over the next few 100 million years before reaching the stable, quiet state we associate with mature solar systems. The most immediate change is the clearing of debris. Although the planets have swept up most of the material in their orbital zones, vast amounts of smaller objects remain, asteroids and comets and smaller fragments scattered throughout the system. These objects are on a variety of orbits, some stable, others chaotic, some destined to remain in place for billions of years, others fated to collide with planets or be ejected from the system entirely. In the inner system, near the rocky planets, there is a population of rocky asteroids, remnants from the planet formation process. Some of these are scattered when their orbits bring them too close to a planet, causing gravitational perturbations that change their trajectories. Others collide with planets, cratering their surfaces, delivering material that the planets had not captured during their formation. This period of heavy bombardment peaks perhaps 600 to 800 million years after the system's formation, in what is called the late heavy bombardment. During this time, the inner planets experience an intense rain of impacts from asteroids and comets. The surfaces of these planets are pockmarked with craters, large and small, as debris accumulated over hundreds of millions of years is finally cleared away. The bombardment is not uniform. Some planets, depending on their location and the dynamics of the system, are struck more frequently than others, but all of the terrestrial planets bear the scars. On worlds without atmospheres or geological activity to erase the evidence, these ancient craters are preserved to the present day, a record of the violent youth of the solar system. For planets with atmospheres and geological activity, the story is different. On such worlds, the craters are gradually erased, filled in by sediment, covered by lava flows, or worn away by erosion. But the impacts themselves have lasting effects. Large impacts can trigger volcanic eruptions, alter the planet's rotation, or even strip away parts of the atmosphere. And importantly, cometary impacts may deliver water and organic compounds to the inner planets, providing the raw materials necessary for life. As the bombardment gradually declines, the planetary system enters a more peaceful phase. The supply of debris has been largely exhausted, either incorporated into planets, ejected from the system, or sequestered in stable reservoirs where it will remain indefinitely. Collisions become rarer, happening on timescales of millions or tens of millions of years rather than thousands. The planets themselves are maturing as well. Their interiors, heated by the energy of formation and by radioactive decay, are slowly cooling. The rate of cooling depends on the planet's size. Smaller planets with more surface area relative to their volume radiate heat away more quickly and cool faster. Larger planets retain heat longer and may remain geologically active for billions of years. On the terrestrial planets, this cooling drives geological evolution. As the interior cools, the magma ocean solidifies completely and a stable crust forms. Heat from the interior, transported by convection in the mantle, drives tectonic activity. On some planets, this may take the form of plate tectonics, where the crust is divided into plates that move relative to each other, creating mountain ranges, ocean basins, and volcanic arcs. On other planets, the tectonics may be different, perhaps a stagnant lid, where the crust is rigid and immobile, or perhaps episodic resurfacing, where the crust periodically overturns in global volcanic events. Volcanic activity is common on young terrestrial planets. As the mantle convects and partially melts, magma rises to the surface and erupts, building volcanoes, covering plains with lava flows, and releasing gases into the atmosphere. This outgassing is crucial for atmospheric development. Water vapor, carbon dioxide, nitrogen, sulfur compounds, all of these are released from the planet's interior through volcanic eruptions, building up atmospheres that may have been lost or never fully formed during the planet's violent formation. The atmospheres of young planets are very different from what they will become. They are thick with volcanic gases, rich in carbon dioxide and water vapor, perhaps with traces of methane, ammonia, and other compounds. The temperature and pressure depend on the planet's distance from the star, its size, and the thickness of the atmosphere. Some planets may develop greenhouse effects, where thick carbon dioxide atmospheres trap heat and raise surface temperatures. Others may lose their atmospheres entirely if they are too small to hold on to them gravitationally, or if the star's radiation is strong enough to strip them away. On planets that retain substantial water, oceans may form. As the planet cools and water vapor in the atmosphere condenses, rain falls on the surface, pooling in low-lying areas, forming seas and oceans. The presence of liquid water is transformative. It drives weathering and erosion, breaking down rocks and transporting sediments. It enables complex chemistry, dissolving minerals, providing a medium in which chemical reactions can occur. And most importantly for the future, it provides an environment where life might arise. But we are getting ahead of ourselves. The solar system is still young, only a few 100 million years old. Life, if it will arise, is still far in the future. For now, the planets are barren, their surfaces dominated by geology, their atmospheres the products of volcanism and impacts, their evolution driven by physical and chemical processes alone. The gas giants in the outer system are evolving as well, though more slowly. These planets are so massive that they retain heat for much longer than the terrestrial planets. Their interiors remain hot, with convection currents in their liquid hydrogen atmospheres transporting heat from the deep interior to the cloud tops, where it is radiated into space. This internal heat, combined with heat from the sun, drives atmospheric dynamics, winds, storms, cloud formation that create the beautiful and complex patterns we see on these planets. The gas giants may also have moons that are geologically active. Large moons, heated by tidal forces from their parent planet's gravity, may have liquid water oceans beneath icy crusts, or active volcanism, or other forms of geological activity. These moons are worlds in their own right, and they may be among the most interesting places in the solar system for the possibility of life. The orbits of the planets continue to evolve, though much more slowly now than during the chaotic early phases. Gravitational interactions between planets cause their orbits to change on timescales of millions of years. Subtle shifts in eccentricity and inclination, slow drifts in the orbital distances. Some of these changes are periodic, oscillating back and forth over long timescales. Others are secular, representing gradual trends that continue in one direction. Most of the time, these orbital changes are small and have little effect on the planets, but occasionally, over millions or billions of years, they can lead to dramatic consequences. Resonances, situations where two planets' orbital periods are related by simple ratios, can amplify orbital changes, potentially leading to instabilities. In some solar systems, such instabilities might cause planets to be collided or to be ejected from the system entirely. In our own solar system, the orbits appear to be stable for billions of years, but there are subtle variations that continue to this day. The asteroid belt and other reservoirs of small bodies also continue to evolve. Gravitational perturbations from the planets cause some asteroids to drift into unstable orbits, where they may eventually collide with a planet or the Sun, or be ejected from the system. New asteroids may be created when larger asteroids collide and fragment. Over billions of years, the total mass in the asteroid belt slowly decreases as material is lost through these processes. Beyond the planets, in the distant reaches of the solar system, lie vast reservoirs of icy bodies, the Kuiper belt and the Oort cloud. These objects are remnants of planet formation, icy planetesimals that were scattered outward by encounters with the giant planets. They orbit in the cold and dark, far from the sun's warmth, largely unchanged since their formation billions of years ago. Occasionally, gravitational perturbations, perhaps from passing stars or from the planets themselves, send one of these objects on a trajectory toward the inner system, where it becomes a comet, growing a bright tail as the sun's heat vaporizes its ices. 1 billion years have now passed since the star was born. The solar system has reached maturity. The planets have settled into stable orbits, their interiors have cooled to the point where geological activity is sustainable at moderate levels rather than catastrophic. Their atmospheres have evolved to reflect the balance between outgassing, escape, and chemical transformation. The heavy bombardment has ended, and impacts are now rare events, occurring on timescales of tens or hundreds of millions of years. The surfaces of the terrestrial planets bear the marks of their history: ancient impact basins, vast volcanic plains, mountain ranges, and valley systems. On planets with atmospheres and liquid water, erosion and sedimentation are sculpting the landscapes, creating features that will change over geological time. The solar system has become a quieter place. The violence of formation is past, the chaos of migration and bombardment has subsided, and what remains is a stable, orderly system of planets and smaller bodies, all orbiting the central star, all governed by the same gravitational laws that shaped their formation.
But this is not the end of the story. It is, in some ways, just the beginning. The planets will continue to evolve, driven by their internal heat, by the energy from the sun, and by the occasional impact or gravitational perturbation. Atmospheres will change, surfaces will be reshaped by geological processes, and on at least one planet, perhaps on others, the chemistry of the surface and atmosphere will become complex enough, organized enough, that life will arise. The star itself will also evolve, though on much longer timescales. For billions of years, it will remain on the main sequence, fusing hydrogen in its core, shining with steady light, providing energy to its planets.
But eventually, the hydrogen fuel will run low and the star will begin to change, swelling into a red giant, perhaps engulfing the inner planets before finally shedding its outer layers and fading to a white dwarf. But all of that is in the distant future, billions of years away. For now, the solar system is young and stable, the planets are formed and orbiting, and the long, slow process of planetary evolution has begun. From nebula to protostar to star to protoplanetary disk to planets, the transformation is complete. The universe has once again demonstrated its ability to create complexity from simplicity, structure from chaos, worlds from clouds of dust. The cycle will continue. Stars will continue to form from nebulae, planets will continue to form around stars, and the galaxy will continue its slow rotation, mixing and recycling material, creating new generations of stars and planets from the remnants of old ones. The process we have followed, from nebula to planets, is playing out right now around countless young stars throughout the galaxy and the universe. And so we end where we began, with nebulae, vast clouds of gas and dust glowing softly in the darkness, slowly collapsing under their own gravity, beginning the long journey towards stars and planets and perhaps someday life. The universe is patient, the universe is creative, and the universe is always building new worlds. In the beginning, there was a cloud, a vast, cold, diffuse cloud of hydrogen and helium and heavier elements, rotating slowly in the darkness of space, waiting for something to disturb its equilibrium. A shock wave came from a dying star's final explosion, compressing the cloud, triggering the cascade of collapse that would transform it utterly. And from that cloud emerged a star, bright and warm, powered by nuclear fusion in its core, destined to shine for billions of years. And around that star formed a disk, a flat carousel of dust and gas, rotating in orderly fashion, following the mathematics of gravity and motion. And within that disk, dust grains collided and stuck together, growing slowly larger, building pebbles and boulders and mountains and moons and planets, each one unique, each one shaped by its particular circumstances. And the planets settled into their orbits, cleared away the debris, matured and evolved, becoming the worlds we see today, or worlds like them, scattered throughout the universe. This is how worlds are born. Not quickly, not through divine intervention or sudden creation, but slowly, patiently, through the relentless application of physical law over millions of years. Gravity pulls matter together, rotation flattens it into disks, compression heats it until fusion ignites, dust accumulates into planets. Every step follows inevitably from the step before, governed by the fundamental forces that shape the universe. And yet, despite this mechanical, deterministic process, the result is breathtaking in its complexity and beauty. No two planetary systems are exactly alike, just as no two snowflakes are identical, despite being formed by the same physical principles. Each system is shaped by countless small variations: the initial rotation rate, the exact composition of the nebula, the timing and strength of disturbances, the random outcomes of chaotic gravitational interactions. Some systems have many planets, others have few. Some have hot Jupiters orbiting close to their stars, others have ice giants in distant orbits. Some have rocky super-Earths, others have nothing larger than asteroids. The diversity is immense, and we are only beginning to discover and catalog it through our telescopes. But beneath this diversity is unity. Every planetary system, every star, every nebula is governed by the same physical laws. The force of gravity that shapes galaxies also assembles planets. The nuclear fusion that powers the most massive stars also powers the smallest. The same chemistry that creates molecules in cold nebulae creates the organic compounds necessary for life. We are part of this story. The earth beneath your feet, the air you breathe, the water in your body, all of it formed through the process we have described. The iron in your blood was created in the core of a dying star and scattered through space in a supernova explosion. The calcium in your bones, the carbon in your cells, the oxygen you breathe, all of it was once floating in a nebula, part of a cold cloud waiting to collapse. We are quite literally made of star stuff, assembled by gravity and chemistry over billions of years, organized into structures complex enough to wonder about our own origins and to tell stories about the universe that created us. And the process continues. Right now, at this very moment, nebulae are collapsing in distant parts of the galaxy. New stars are being born. New planetary systems are forming. The universe is always creating, always building, always following the same patient path from clouds to stars to worlds. Perhaps around some of these new stars, planets are forming that will someday host life. Perhaps billions of years from now, beings on those planets will look up at their night sky, wonder about the stars, and eventually come to understand the same story we have told here, the story of how worlds are born from nebulae, patiently and inexorably, following the ancient laws that govern all things. The universe is vast beyond comprehension, old beyond human timescales, and yet it operates according to principles we can understand. Gravity, nuclear fusion, thermodynamics, chemistry, these are not mysteries, but mechanisms, tools the universe uses to create complexity from simplicity. And so we return one final time to our nebula. It is still there, glowing softly in the darkness, though it has changed. Where once there was a uniform cloud, now there are stars and planets, systems of worlds orbiting their central lights. But around those stars, new clouds are forming, enriched with elements created in stellar cores, ready to begin the cycle again. The nebula is both beginning and end, destruction and creation, the place where old stars scatter their atoms and new stars gather them up again. It is the engine of cosmic renewal, the birthplace of worlds, the source from which all things come, and to which, eventually, all things return. Rest now. The universe is patient. The stars will still be shining tomorrow, and the nebulae will still be collapsing, slowly and inevitably, creating new worlds in the darkness. The cosmic dance continues, as it always has, as it always will, turning clouds of dust into planets and stars and galaxies, building the universe one atom at a time. The story of how worlds are born is complete. From nebula to planets, we have followed the path of creation, watched as gravity and physics work their slow magic, transforming the simple into the complex, the diffuse into the concentrated, the cold and dark into the bright and warm. Sleep well, knowing that you are part of this story, a temporary arrangement of atoms that once drifted in a nebula, were forged in a star, assembled into a planet, and organized into the complex structure of a living being capable of understanding and appreciating the journey that created you. The universe is vast, but you are part of it. The time scales are incomprehensible, but they led to this moment. The processes are impersonal, but the result is beautiful beyond words. From nebula to planets, from clouds to worlds, the journey is complete. Rest now and dream of stars.